In lesson 10.1, we're learning about one method of solving a system of two linear equations, and then we're also going to advance to solving linear inequalities in two variables. This video will be focused primarily on the solving of systems of two linear equations. So our first target is what we're addressing here, and that is that we want to solve systems of two linear equations by graphing. When you're finding a solution to a system of two equations, what we're looking for is what those two equations have in common. So if there's a solution that is a solution to the first equation, it will also be a solution to the second equation. And basically, we've got three scenarios that might exist. Either there is one solution, like we see here in case 1. We have one linear equation, another linear equation, and those two linear equations meet in one place when we graph them. That is a situation where we have one solution to our system of linear equations. Case 2 demonstrates a situation where we have two linear equations, but they both have the same slope, but different y-intercepts. So therefore, when we graph them, they are parallel lines. We've talked about this in a previous lesson. Well, in that case, those two linear equations have no points in common, therefore there are no solutions. The third case is where the first linear equation is an equation of a line that produces the same exact line as the second equation. So basically what that means is that those lines lie on top of one another, and therefore there are an infinite number of solutions to that linear equation, or to those linear equations. Now, with regards to case 2 and case 3, case 1 is pretty obvious. There's one solution, so you'll find one x value paired with one y value that will be a solution to that system of equations. Case 2, though, there are no solutions, and so we would say so, and we call that an inconsistent system. When they're parallel, never meet one another, we have an inconsistent system. Case 3 is where everything that is on one line is also on the other line, and we call that a consistent system. But it is a special kind of consistent system, and we call it a dependent system. That didn't come through very clearly here on my slide, but it is very clear on the PowerPoint that I have loaded in Canvas for lesson 10.1. So we have either 1, a consistent system of linear equations, or 2, an inconsistent system of linear equations. And a consistent system of linear equations can be one in which there is either one solution, because the two lines meet in only one point, or 2, there are infinitely many solutions in which the lines lie on top of one another, and we refer to it as a dependent system of linear equations. So what we're going to do here is we're going to work through an example where we want to determine the solution or solutions, or lack thereof, of our system of linear equations. So if we look at my first example here, we see that we have two linear equations that are both in standard form. Standard form, we remember, is in the form ax plus by equals c. And we've learned that the easiest way to determine the graph of an equation in standard form is to find its intercepts. So I'm going to do just that. First equation here, I'm going to find its intercepts. I'm going to plug 0 in for x and find y. So notice all that I did was replace the x with 0, and so I get 0 minus y is negative 2. Therefore, minus y is equal to negative 2. So positive y is equal to positive 2. So basically, we have a point on that line where x is 0 and y is 2. Now we're going to find the y-intercept. The y-intercept is found by substituting 0 in for, we just found the y-intercept, excuse me. The x-intercept is what we're going to find next, and so we're going to substitute 0 in for y. Obviously, that will produce the equation 2x equals negative 2, and when we divide both sides by 2, we find that x is equal to negative 1. So another point that's on that line is where x is negative 1 and y is 0. And that's because we substituted 0 in for y. So we're going to graph that line here, and we're going to see that that line crosses through the point 0, 2 and negative 1, 0. Now we need to do the same thing for our second equation. So to find the x-intercept, I'll plug 0 in for y and solve for y. And what I'll find for x equals 8, so x must equal 2. So when I substituted 0 in for y, I found x was 2. Now, the y-intercept. I'll plug 0 in for x. Obviously, 4 times 0 is 0, and 0 plus y is y, so y must equal 8. So when we substituted 0 in for x, we got y equal to 8. So again, we're going to find that we can graph that line easily by connecting the points at 2, 0 and 0, 8 to one another and drawing a line through them. And here we see the result of our system of equations. So the blue line is the first equation, 2x minus y equals negative 2. And notice we plotted the y-intercept, which doesn't completely show in this picture. We also plotted the x-intercept of 2. And we drew a line through those 2 points, and that formed the line. I think I may have misspoken. Give me a sec. So the 2x minus y equals negative 2, we determined that the y-intercept was at 0, 2, and that the x-intercept was at negative 1, 0. And so you notice that the blue line has a y-intercept at 0, 2, and it has an x-intercept, that's this point right here, at y-intercept at 0, 2, and then it has an x-intercept at negative 1, 0. So we plotted those 2 points and drew a line through them. The red line is for the other equation, 4x plus y equals 8. We found that it has a y-intercept of 8, which doesn't appear on my screenshot here, but it has an x-intercept at 2, 0. So we plotted that, and we drew a line through those 2 points. Now the solution to this system will be the place where those 2 lines meet one another. And in this case, we can see that the point at which these 2 lines meet one another is the point 1, 4. Now, just to verify, if we substitute 1 in for x in the first equation and 4 in for y in that equation, we get 2 minus 4 is -2, and that is a true sentence, so it works. That solution is in fact a solution to the first equation. If we substitute 1 in for x in the second equation and 4 in for y in that equation, we do find that it works. 4 times 1 is 4, 4 plus 4 is 8, and 8 is equal to 8. So we can always check our solution to a system of equations by plugging the x coordinate into the equation and its corresponding y coordinate and make sure that the two sides come out equal to one another. So here we've demonstrated the first example of solving a system of linear equations by graphing. Now this is an example of a consistent system of equations. What makes it consistent is that it has at least one solution.